unfortunately, we weren't able to in person again today, but hopefully we'll still hear lots of interesting talks online. So this morning, Jörg is going to start again, and he's going to continue his lectures on introduction to relativity. So maybe you're ready.
Okay, thank you very much, and good morning, everyone. Now, first of all, like yesterday, I've got a handout for you which contains all the text for the 2 GR lectures today. So I just post the link in the chat. So if you're interested, then you can download the PDF and have all the calculations and equations available. And now I try to share my screen. So hopefully you can see my screen now. Now, let's continue where we stopped yesterday. We have worked out Einstein's field equations, and let me just quickly remind you, we have GAB, the Einstein tensor, possibly plus in this term, lambda, the cosmological constant times the inverse metric, is equal to 8 pi TAB, where TAB is in the energy momentum tensor, and 8 pi is just the Einstein gravitational constant in geometric units, where G and C are equal to 1. So the second term, the cosmological constant, that's maybe relevant for cosmological calculations, not so much if you want to describe something local, like, say, the field of a star or a black hole. Now, if you look at these equations, we have 2 indices A and B, and all objects here are symmetric. And we just discussed before, symmetric tensors in 4 dimensions have 10 independent components. You can choose the diagonal and everything above the diagonal, and the rest is then fixed, which gives 10 degrees of freedom. So this system here actually corresponds to 10 coupled partial differential equations. And they are rather complicated. They are nonlinear, as you are already aware of, because if we want to compute the Einstein tensor, we have to start from the metric, then work out the Christoffel symbols, which also involve the inverse metric. And the inverse of a 4x4 matrix already is a complicated expression in terms of the original metric. So you can imagine that once you go to the Riemann tensor and the Ricci tensor, you end up with rather complicated functions in terms of the original metric components. So it's a very involved system of equations. And indeed, in general, one only can find solutions by applying numerical methods, as you heard about. But how could we possibly also obtain exact solutions? It's, of course, always nice. If you have some explicit formula describing a solution, then it's easier to study details of the behavior of the solution. Now, the only chance seems to be that you make some simplifying assumptions. You could start with on the right-hand side and choose a reasonably simple meta model where the energy momentum tensor is not too complicated. Maybe you want to look at dust solutions where the pressure is equal to 0, or probably even just consider vacuum where there's no energy momentum at all. So TAB at all is equal to 0. Even vacuum gives interesting solution because just consider the gravitational field outside the source, the field around a star, for example, or a vacuum region where gravitational waves are passing through. So in general relativity, even vacuum can be very interesting. And in order to simplify the left-hand side as well, usually in order to really find exact solution, one has to make the assumption that we are looking for symmetric solutions, maybe something that is spherically symmetric or has some other symmetries. In this way, we can reduce the number of degrees of freedoms and the number of independent components in the metric that we have to find, and also reduce the number of independent equations. Now, in today's lecture, I will give you 2 examples for this. I will show you in some detail how we can actually obtain the Schwarzschild solution that you already heard about, and also look at a simple but practically quite relevant cosmological model, which already shows that our universe seems to have started from a Big Bang, and that nowadays, if there is a positive cosmological constant, we could expect a phase of accelerated expansion as we actually observe it nowadays. Let's start at the Schwarzschild solution. So partially, I need to repeat a few things that you heard already in other talks from Susan, for example, yesterday. So this solution is from 1916 by the German physicist and astronomer Karl Schwarzschild, or more precisely, I think it was derived in 1915 already and published in early 1916. So just shortly after Einstein published his field equations for general relativity, this exact solution was found. So this was probably the first non-trivial exact solution to Einstein's field equations, maybe apart from Minkowski spacetime, which is really trivial, but the first somewhat more interesting solution. Now, this solution describes the vacuum region. So it's a vacuum solution. The right-hand side of the Einstein equations is equal to 0. outside any spherically symmetric matter distribution. So for example, if you take a spherically symmetric star like our sun and you want to describe the exterior gravitational field, then this is given by the Schwarzschild solution. So if we want to obtain this solution, then we have to solve this task, construct a spherically symmetric vacuum solution, and we assume for that purpose that lambda is equal to 0. We don't look at the cosmological constant term. Now, in order to see what kind of structure our metric should have, let's first look at the following. Assume you have just a flat three-dimensional Euclidean space, and you consider a two-sphere, so the two-dimensional surface of a three-dimensional ball, which has some fixed radius r. In order to describe this, you could start from Cartesian coordinates x, y, z, and then in the usual way introduce spherical coordinates. Just here, r itself is not a variable, but it's just the constant radius of the sphere. So the only degrees of freedom are theta and phi, r is fixed. Then you can work out what dx is in terms of d theta and d phi by just differentiating this equation. And if you do this, you get this linear combination of d theta and d phi, and you can do the same for dy and dz. And if you now plug everything into the very simple line element for a flat three-dimensional space, dx squared plus dy squared plus dz squared, then the initially complicated expressions simplify using trigonometric identities, and all that remains in the end is in this expression r squared, which is a constant. It's a sphere of constant radius, and we have d theta squared plus sine squared theta d phi squared. So that's the line element describing a two-dimensional sphere, and because we are looking now for a spherically symmetric solution, our four-dimensional metric should also have a term which looks like this. So what we want to do now in the relativistic context, we want to construct a four-dimensional spacetime, of course. We can still introduce a kind of spherical coordinate system. So let's say our coordinates are a time coordinate t, a radial coordinate r, and angles theta and phi. And we want to achieve that if we consider a slice of constant time and r at a constant radius, then we really just reduce our four-dimensional metric to the two-dimensional line element for a sphere that I just showed you. So we could say that it's reasonable to look for a metric of this form. We have terms which are proportional to dt squared, dt dr, and dr squared. So when t and r are constant, this all vanishes. And this coefficient here is also constant if t and r are constant, and then we really just get the usual line element for a two-sphere. But then, of course, if t and r are not constant, we take some other terms into account. But all these functions here, a, b, c, d, are functions of t and r only. So because of the spherical symmetry, they should not depend on the angles theta and phi. So it's plausible to assume that we are looking for a four-dimensional metric of this form, and one can do some more careful mathematical discussion why the metric actually should look like this. Let's just assume it's reasonable because it reduces to the geometry of a two-dimensional sphere if t and r are constant. So to begin with, we have to find four unknown functions, a, b, c, and d, which are functions of two variables, a time coordinate t and a radial coordinate r. Now, in general relativity, we always have the nice situation that we are free to choose coordinates however we like. So sometimes we can just change our coordinates a little bit in order to simplify the situation. So as it turns out, some of these degrees of freedom here are actually just related to our freedom of coordinate choice. And if we specialize our coordinates further, we can simplify the situation. First of all, whatever function d of t and r we have here, we could say we replace the radial coordinate capital R in favor of a new radial coordinate little r by just saying r squared is equal to this expression. Now it's safe to define this to be a square of a quantity because this coefficient of the spatial part should have a positive sign. So we can compute the square root of d, and this would define the new coordinate r. Now then you can work out if you differentiate this expression or calculate differentials, 2r times dr on the left-hand side will be equal to the derivative with respect to t times dt plus the derivative with respect to r times dr. So in this way, you can replace the d capital R in terms of a d little r. And in particular here, this coefficient d just becomes r squared, and the other metric coefficients change a little bit. So I call them now lowercase a, b, c. But it has a similar structure. And now we have simplified this term here, and we just end up with 3 degrees of freedom. So just by making a coordinate transformation, we remove one of the unknown functions. Secondly, this mixed term here, dt, dr, is a little bit annoying, but it turns out we can just make a further coordinate transformation to get rid of this term as well. We can introduce a new time coordinate little t, so replacing our time coordinate capital T. What we first may think we could do is we could try to introduce this new time coordinate t in such a way that dt is equal to some coefficient times d capital T minus another coefficient times dr, and these coefficients are chosen in such a way, if you would replace the d capital T like this, that the mixed term disappears. But in general, a linear combination of two differentials will not define the differential of another function. So if you didn't have this coefficient here, then you would not generally find the function t such that the capital T derivative is equal to this coefficient and the r derivative is equal to that coefficient. So for that reason, we have to introduce this integrating factor here. If we introduce another free function here, then we can always find it in such a way that this total object really is in the differential or is equal to the linear combination of these two differentials. And now you can just work out what the coordinate transformation is looking from this relation of the differentials. And the main thing is if you now solve for dt and replace the dt and dt squared here like this, then the metric simplifies. And after this transformation, we don't have a mixed term, which is dt, dr, like this one here. We just have a dt squared and a dr squared. And from this coefficient here, we also get this minus e to the new term, and I now call the coefficient of the dr squared term e to the lambda, some function of t and r. So it's convenient to introduce a name here for the exponents and not for the full functions, because the equations look somewhat simpler in terms of the exponents. So just by using these two coordinate transformations, we have reduced the number of available free functions to 2. We have a function u of t and r and a function lambda of t and r. And if you read off these coefficients in the metric as a matrix, looks like this. It does have this diagonal structure. So what we need to find are these two unknown functions, nu and lambda. Now, in order to do this, starting from this structure of the metric, the usual procedure is that you first work out the Christoffel symbols, then you calculate the Riemann tensor, and afterwards the Ricci tensor, and then you can work out the Einstein vacuum equations. So that's the definition of the Christoffel symbols. And now you can ask yourself, for what possible combination of the indices a, b, and c do you get something that is non-zero? There are somewhat more systematic methods to do this, but let's say you just try out all possible combinations, then you will find there's a whole bunch of these Christoffel symbols which is not equal to 0, and everything else that is not listed here, this is equal to 0. So these Christoffel symbols depend on our two unknown functions, nu and lambda, and I've introduced the notation a dot here, like here refers to the time derivative, and a dash to the derivative with respect to the radial coordinate r. So there's a good bunch of Christoffel symbols which are not equal to 0. And from these, we can now work out the Ricci tensor in the next step. So the Ricci tensor was just the contraction of the Riemann tensor like this. And using the formula for the Riemann tensor, inserting this contraction, we get this explicit formula for the Ricci tensor. And once again, you can work out all possible index combinations for A and B and test where you get something non-zero. And it turns out these are the surviving expressions. We have a TT component, an RR component, and a T phi component, which is the same as phi here. The Ricci tensor is symmetric in the two indices, and a theta theta component. There's also a non-zero phi phi component, but that's not so interesting because it's just proportional to the theta theta component, and because we anyway want to impose the Einstein vacuum equations. So then it's automatically guaranteed if this component vanishes, this multiple vanishes as well. So altogether, we have 4 independent components, which give some non-trivial results. We have to look at 4 equations. So we want to solve the Einstein vacuum equations. We assume that lambda is equal to 0. So we have to solve the equations RAB is equal to 0. Or equivalently, you could say the Einstein tensor GAB is equal to 0. But here, because we already have the Ricci tensor, it's easier probably to directly look at this form of the vacuum equations. Now, first of all, it turns out that one of our 2 functions, lambda, must be time independent. Initially, we have assumed the function can depend on time. And indeed, we have looked at a spherically symmetric matter distribution. I have not said it's supposed to be a static distribution. For example, think about an oscillating star where the radius becomes bigger and smaller periodically. Then the matter distribution would depend on time. but still it turns out our function lambda will be time independent. So one of our components of the Ricci tensor was this one, and if this is supposed to be equal to 0, then obviously lambda dot, the time derivative must vanish, which can only mean that lambda must be a function of r only. So that's the first simplification. One of our functions does not depend on time. Secondly, we can also achieve that nu is time independent. Another component of the Einstein equations, or this component of the Ricci tensor, was this expression. And now, since we know lambda is a function of r only, then this coefficient as well as this derivative depend on r only as well. Here, this r obviously depends on r only. So that can only equate to 0 in this combination if nu dash is a function of r also as well. This does not quite tell us immediately that nu is a function of r only. We first get that nu must have this structure as some function of r, possibly plus some function of time. And if you compute the radial derivative nu dash, then this function of time disappears. So then it's guaranteed nu dash will be a function of r only. But it turns out this function of time is just a coordinate degree of freedom that we can eliminate by another coordinate transformation. The function nu only appears in the form e to the nu dt squared in our metric. And if you plug in that nu is this linear combination of a function of r and a function of t, we get two factors, one which depends on r, another factor which depends on t times dt squared. Now we can just say we want to achieve that these two factors together are equal to some dt dash squared and introduce a new time coordinate t dash, which is a function of the old time coordinate t, and you can work out a differential equation which needs to be satisfied by this coordinate transformation. And after we've done this, we have effectively eliminated this function f of t by changing our time coordinate accordingly. And afterwards, of course, we can just rename the variable t prime into t. So effectively, we have removed this function f of t, we have absorbed it into a slightly changed time coordinate. So what we find is not only the function lambda, but after a suitable coordinate transformation, also the function nu is time independent. So we obtain that both of our functions are functions of r only, and therefore the entire metric is time independent in these adapted coordinates. This results in this important theorem known as Birkhoff's theorem. Every spherically symmetric solution to the Einstein vacuum equations is independent of time. One would also say the solution is static. It may still be that, say, our star, where we want to describe the exterior field, is probably oscillating. It may be time dependent, or it's maybe collapsing or expanding, but still the field around the star will be time independent. So that's an important observation. Even a time dependent source would lead to this exterior vacuum field, which is time independent. And this in particular shows a spherically symmetric source, even if it depends on time, cannot cause gravitational waves, because the vacuum region would be time independent. It cannot oscillate in time. Okay, if we now use that both of our functions are functions of r only, then our field equations reduce to these three ODEs. So the next task is to explicitly find out what are the functions nu and lambda as functions of r. Now, firstly, if we look at the second equation, if we just integrate this, we immediately find nu is equal to minus lambda, possibly plus an integration constant. But once again, such a constant in nu just leads to an additional factor in front of the dt squared, and you could once again rescale your time coordinate to absorb this integration constant. So we can just safely say nu is equal to minus lambda without any integration constant. So firstly, we have reduced the 2 degrees of freedom to just 1. We just have to find, say, the function lambda, and the nu is just given by the negative. For that purpose, we can have a look at this third equation, which depends on lambda only. And this can be solved if you make this substitution, if you replace e to the minus lambda by some function alpha, because in terms of alpha, this becomes a very simple equation. It's a linear first order ODE with an inhomogeneity. So you could easily solve the inhomogeneous problem first and then find a particular solution to the full problem. And in this way, you will obtain alpha, which is e to the minus lambda, is given by 1 minus 2m over r, where m is some integration constant. Initially, this m would just be an arbitrary constant, but later on, it does turn out that this is actually the mass of the central body, the mass of the space-time. Mass is a little bit of a complicated concept in general relativity, but let's just say there's one particular mass definition where this parameter m is really equal to the mass of the spacetime or the source, say the star in the spacetime. So that's the function e to the minus lambda. In our metric, we have here the e to the lambda, so that's the reciprocal of this, and the nu is just minus lambda, so that's equal to e to the nu. Therefore, we get this coefficient here in front of dt squared, and we have recovered the famous Schwarzschild solution, which we have already encountered in several other presentations here. So that was the systematic approach to solve Einstein's field equations and taking advantage of our freedom to do coordinate transformations in order to find an expression which is as simple as possible for our final result. Now we can immediately see an interesting property of the solution. If R is large, if R goes to infinity, if we are very far away from our gravitational source, then 2m over R goes to 0. So the metric reduces to just minus dt squared plus dr squared plus this term here. And this is just the well-known Minkowski metric expressed in spherical coordinates. So we can see if we are sufficiently far away from the gravitational source, say from our star, then the solution becomes very simple and just approaches the flat Minkowski spacetime. So because of this, the solution is also called asymptotically flat. Next, it's interesting to study geodesics in the Schwarzschild solution, which describe either the motion of test particles or of light. Let's first have a look at test particles, and in this way we can recover the famous perihelion shift. Now, if you want to describe the motion of test particles, then we should look at time-like geodesics, because test particles move on geodesics where the tangent vector, the forward velocity, is a time-like vector. And if I say test particle, this could even describe the motion of planets in the gravitational field of Sun, because the mass of the planets is much less than the mass of Sun. So the planets don't have a strong influence on the gravitational field and can really be treated like test particles that move on geodesics in the field of Sun. So we can use or study the geodesic equation, which looks like this. Tau is the proper time, and if we parameterize our curves in terms of the proper time, then we already know the tangent vector, UA, that's just the forward velocity, which satisfies this usual normalization condition. It's a vector normalized to -1, so the minus sign in my convention indicates this is a time-like vector. Now there's another approach. You could also so for this approach, you would now need to start again computing the Christoffel symbols, which we looked at before, and then you can work out the components of this equation. Let me just point out, there's also a somewhat quicker approach where you start directly from the metric, write down an appropriate Lagrangian function, and then the Euler-Lagrange equation for this Lagrangian give you directly the geodesic equation. So that's maybe a slightly faster calculation. You don't have to use the formula for the Christoffel symbols. And indeed, you can use this approach to work out the Christoffel symbols. But because we haven't talked about this, let's just say you use all these expressions for the Christoffel symbols that we discussed before. Now, this is actually a system of 4 equations, because the free index A here can take on 4 different values. So what we get is these 4 equations. The first term here always contains a second-order tau derivative. So the dot here now refers to a tau derivative. And the other expressions here come from the Christoffel symbol terms. So we have to study these 4 equations. Now, first of all, we can make the following simplification. You may choose your spherical coordinates, your angles theta and phi, in a suitable way. So let's say the test particle, the planet that we want to describe, is initially located in the equatorial plane, where theta is equal to pi12. And we have rotated this plane in such a way that the change of theta initially is equal to 0. That's what we can always achieve if we just appropriately redefine our angles, if we rotate our spherical coordinates. But then we know the initial value of theta and theta dot, so that's already enough to solve this second-order differential equation for theta. And you can easily check this has the solution that theta is identically equal to pi12, because then the theta derivatives vanish and the cosine of theta also gives 0, so everything is equal to 0. And the second-order differential equation will have a unique solution if you specify these initial conditions. So we can be sure, if we choose our coordinates in such a way that initially we are in the equatorial plane, the test particle will at all times be confined to the equatorial plane. So it's just convenient to rotate our spherical coordinates in such a way that the motion happens in the plane theta is equal to pi12. Now, if we do this, then we can simplify our first and fourth equations, it would actually be easier to see the following if you would start from this Lagrangian approach, where there's always some relationship between a special structure of the Lagrangian and conserved quantities. But even looking at these equations, you can confirm this equation here is equivalent to the statement that this time derivative vanishes if you just apply the product rule and afterwards divide the final result by e to the nu. You end up exactly with this equation. And similarly, if you work out the derivative here, then you get this equation now plugging in that theta is equal to pi half. So this term would disappear. So we can integrate these two equations or write them as derivatives of some functions, which means these two functions must be constant if their derivatives vanish. We have found two conserved quantities. So let me call them A and B. So if you plug in the explicit form of e to the nu, which was the 1 minus 2m over r, then this equation here tells us that this object must be constant. And from the second equation, we get that this must be a constant b. So we've introduced two integration constants a and b. That's convenient because now we have reduced the problem to looking at two first-order equations. Now, what we eventually want to achieve, if we directly solve the geodesic equations, we would find our coordinates t, r, and as well as theta and phi as functions of some parameter like the proper time. But in order to study what the orbit of a planet looks like, it's more convenient to obtain the result in the form r as a function of phi. So we see for different angles what is the distance of the planet to the center to r equals 0. So in order to obtain the solution in this form, we can do the following. First of all, the equations simplify if we introduce an abbreviation for the reciprocal of r, if we say call u 1 over r. Then we have the following. From our first conservation equation on the previous page, or actually the second one, if you solve this for phi dot, you find phi dot is b, our constant, over r squared. And because 1 over r is now u, this translates into b u squared. Similarly, from the other conserved parameter a, you get this expression for t dot. You can work out a formula for r dot if you just use r as 1 over u. And if you differentiate and afterwards consider u to be a function of phi, so using the chain rule, you first differentiate u with respect to phi and correct by multiplying by phi dot. You can express r dot as well. And phi dot, according to our first equation, is just b u squared. If you plug this in, the u squared cancels and you get this expression here. And theta dot is just 0 because we have assumed we are in the equatorial plane, theta is constant. So we have found expressions for phi dot, t dot, and r dot. And now we can simply plug this into our normalization condition. The forward velocity, which is given by this explicit expression, must be equal to -1. So if we do this and multiply the final equation by 1 minus 2m over r, we get this expression here. So because of this multiplication, the right-hand side is not equal to -1, but 1 minus 2m over r, which is the same as 2mu. And on the left-hand side, for example, from our metric coefficient g(t), if a and b are equal to t, we get a -1 minus 2mu. And I also plug in the t dot squared, and t dot gives an a squared. And I get this factor squared, which cancels the coefficient after multiplication by 1 minus 2mu. And similarly, if you plug in the r dot term and the phi dot term, you get in these other terms. So it's just plugging everything what we have here into our normalization condition. And this now is a first order equation for u. And here we have the derivative of u with respect to phi as well, a first order differential equation for u. Now, in principle, you can solve this equation directly, but not, unfortunately, in terms of elementary function. You encounter elliptic integrals and need to solve this in terms of special functions. So to make this a little bit easier to see more directly what happens, we can differentiate this equation again. If we differentiate this first order equation with respect to phi, then we end up with something which contains also a second order phi derivative. But it has a somewhat simpler structure because the left-hand side of this equation is just linear in u, unfortunately not in the right-hand side where we have this u squared term. So now we want to solve this equation approximately. If we didn't have this u squared term, if we would just have the first three terms here, then you could easily solve the equation. Then it would really just be a linear equation which has a constant inhomogeneity, and you would find, if you denote this function by u0 as a function of phi, referring to just the simplified equation that's given by this expression. Now, you may have encountered this expression before, so recall that u is 1 over r, so r itself as a function of phi would be given by a constant divided by 1 plus epsilon cosine phi, and that's just the representation of an ellipse in spherical coordinates, where the center of the coordinates is in one of the focal point of the ellipse. So that's the description of an ellipse, or in fact of any conic section, depending on the value of epsilon. This can also describe hyperbolae and parabolas. So we find the Newtonian situation that planets are moving on ellipses and other objects can move on hyperbolae. So that's what we find without this u squared term here. We recover just one of Kepler's laws. The planets are moving on elliptical orbits. Now, in order to solve the full equation, but just approximately, let's assume that m over r is much less than 1. Now, this applies very well in our solar system. If we use geometric units, then the mass of our sun, we have heard this in other presentations, is about 1.5 kilometers. So we just have to make sure that we are looking at planets where the orbit is much further away from r equals 0 than 1.5 kilometers. And that is certainly true for all kilometers. Our sun has a radius of 700,000 kilometers. So even to ensure that we are outside sun, we already have to choose r sufficiently large. So certainly m over r for any object in the solar system will be much less than 1, and this approximation is justified. Now we can try to solve this full equation by just plugging this approximation u0 in for the unpleasant quadratic term. So we solve this equation for u, where now this term is specified because we plug in our approximation here. So now we have a known inhomogeneity here and just have to solve this equation for u. Now it turns out you can do this exactly, and the full solution is equal to our approximation u0 plus this small correction. Now this correction actually is small. You can easily check if you assume m over r is much less than 1 and u scales like m over b squared, that means r, which is the reciprocal, scales like b squared over m, then if you plug this into this inequality, you find that that m squared over b squared must be much less than 1. And then it turns out that this coefficient here, the m cubed over b to the fourth, is much less than u0. So we see our solution has in the structure, it's equal to a large part u0 plus a small correction given by this term here based on this assumption. Now, if you look at the terms in brackets here, these terms are just bounded, either constant or oscillating with phi, and this term here grows linearly with phi. So the most important term is in this one here, and for our approximation, because this coefficient is anyway small, we can ignore this term here. Obviously, you could also study the full expression, but just to see very clearly what effect we get, let's simplify this as much as possible. So let's ignore this term here. Next, if we plug explicitly in what u0 is, namely this expression here, we get this formula here, where here we have this additional correction, and the coefficient here is much less than 1. And epsilon, by the way, is the eccentricity of the orbit describing our ellipse. Now we can further simplify this expression. We could also study this expression now, but in order to see very clearly what is happening, we can use the following reformulation. Rather than having a cosine and a sine here, we can write this as a cosine of just one expression, where we have a number slightly less than 1. Recall that this coefficient here is much less than 1, a number slightly less than 1 times phi. So effectively, we have the cosine of a difference of two angles, cosine of phi minus the small number times phi. And if you take this apart with a trigonometric identity and use this coefficient is very small, then you exactly recover these two terms here. Now this now almost looks like a Newtonian ellipse. It's very similar to this expression here. Just in front of the phi here, we do have this additional factor, which is not exactly equal to 1 like here, but slightly less than 1. So let's study how this equation here with this factor slightly less than 1 actually looks like. Now you see if phi is initially equal to 0 and then increases to 2 pi, the argument here is not yet at 2 pi because this coefficient is slightly less than 1. This means phi needs to increase a little bit more to make sure that you complete the orbit and the argument of the cosine has reached 2 pi. So the function here is not 2 pi periodic. Instead, if you plot this function, you get something like this. This corresponds, say, to sun at r is equal to 0. And then we don't quite have ellipses, but actually something that rotates a little bit. So here, this red point where, say, the planet is furthest away from sun, and the next point where this happens are rotated by a certain angle delta phi. So let's have a look what this angle delta phi must be. If we initially consider phi is equal to 0, where the argument of the cosine vanishes, then the next time the argument of the cosine, or the next time when this reaches 2 pi is not quite when phi is equal to 2 pi, but because this factor here is less than 1, we need to increase phi a little bit more. Say we need to have 2 pi plus delta phi, some small angle, namely this angle here. And then you can just plug in that this structure of phi is supposed to be equal to 2 pi, and then approximately you find delta phi needs to look like this. So that's the additional angle that we need in order to make sure that the argument of the cosine reaches the value of 2 pi. And this formula here is given in terms of our conserved quantity b, which is not so convenient. But if you just look at the original formula for our ellipse, you can read off this describes an ellipse which has this semi-major axis a. And then you can use this formula in order to replace the b squared here in terms of these other quantities. So if you do this, then you get a formula for delta phi, which just depends on measurable quantities, namely the mass of the central object, mass of sun, for example, the semi-major axis of the orbit, and the eccentricity of the orbit. And if you want to, you can always restore the factors g and c, which in our units are equal to 1, and convert this back into standard international units. Then you get this additional factor g and the c squared term. You can always just multiply by an unknown power of g times an unknown power of c and fix in the exponents from the requirement that you get the correct physical units in SI units. So then you recover the missing powers of c and g. So that's how this formula looks like, including these factors. So this is called the perihelion shift. I should just point out what I've shown in my picture here. These two red points are the points where the planet is furthest away from sun, which is not quite in the perihelion, but in the aphelion. The perihelion here would be the closest point to sun. But if the entire ellipse is rotating by the amount delta phi, then both the perihelion and aphelion rotate by the same amount. So even though it's easier to illustrate the aphelion in my picture, the same applies to the perihelion shift. If you apply this in our solar system, then how can you see the largest effect? Well, the effect is proportional to the mass of the central object, but we don't have any control over this. We just have one sun, so we need to take whatever m we get. But then the effect also is largest if a is as small as possible, and therefore we should look at the planet which is closest to sun, which obviously is Mercury. And it also helps if the eccentricity is less than 0, then this further increases in this effect. So if you plug in the parameters for Mercury, then you find this angle delta phi is 0.1 arc seconds. So just recall an arc second is a fraction of 1/3600th of a degree. So a very small amount for one orbit, which takes 88 days. Now, during 1 century, this accumulates to an effect of 43 arc seconds. And that's indeed the relativistic perihelion shift that we can now find from our calculation here. Now, how does this correspond to observations? If you actually measure the perihelion shift of Mercury, you find that's a much larger number of about 575 arc seconds per century. But this is mainly due to the influence of other planets. So here we have assumed we just have sun and one planet. Then we get the effect of 43 arc seconds. In reality, the orbit is also distorted because of all the other planets. And even before general relativity was known, this was a well-known effect. And even before the age of computers, people have done very careful calculation and worked out the effect of other planets explains 532 arc seconds per century. And there was a difference between these two numbers of exactly 43 arc seconds. So it was one of the great successes of Einstein's theory that it could explain exactly these missing 43 arc seconds in the perihelion shift. So keep in mind, the perihelion shift of Mercury is actually much larger than 43 arc seconds, but most of this can be explained in terms of the influence of other planets. And just the small missing amount of 43 arc seconds per century is the relativistic effect, because in relativity, even without other planets, the orbits are not quite close, and we get this perihelion shift. Next, we can also look at null geodesic and describe the motion of light. And in this way, we obtain the effect of light deflection. Now we have to solve the same geodesic equation as before with just two minor differences. First of all, it's not possible to define a proper time for the motion of light. Instead, we choose another parameter for our curves, which is then called an affine parameter lambda. And the tangent vector to the curve is then not a time-like vector anymore as for particles, but a null vector. Light propagates in null directions. Now we can repeat our previous calculation and we obtain the same geodesic equation. So once again, we can choose coordinates where the orbit of the light or the trajectory of the light is confined to the equatorial plane. And we can work out the equation, which will be almost the same. Previously, for particles, we had this equation here. And if we again introduce the u, which is equal to 1 over r, now we get almost the same equation, just this first term is missing. That's just coming from the fact that our tangent vector is normalized not to -1, where we got this term from, but to 0, where this term vanishes. So we just end up with this equation. Once again, we can apply a similar approach to approximately solve this equation. First of all, is if the u squared term would not be here, you get a very simple equation, which is just solved in terms of a trigonometric function with two integration constants d and phi 0. This looks a little bit complicated in polar coordinates, but as soon as you introduce Cartesian coordinates, you see this translates into this equation, which obviously is just the equation for a straight line. So clearly, if there is no mass, if the right-hand side is equal to 0, then light just propagates along straight lines. And this integration parameter phi 0 just corresponds to the orientation of the straight line in our coordinate system. Now, in order to find an approximate solution, as before, we can just plug the lowest order approximation into the right-hand side here, and then solve for the u that we still have on the left-hand side. For that purpose, we can just rotate our coordinates in such a way that this integration constant, this angle phi 0 is equal to 0 to simplify the situation. And then our solution takes on this form. So we get the lowest order approximation plus this correction here. And we just have to make sure that we restrict this to an appropriate range of the angle phi. We should consider phi only in an interval between minus a small angle delta phi and pi, because we need to achieve that u is greater than or equal to 0. Recall that r, our radial coordinate, is 1 over u, and r should not be negative, so we also should not allow values of phi where this formally becomes negative. You can see if you plug in phi is equal to pi, then the sign vanishes, the cosine gives -1, so this term vanishes as well, then this is 0, and for a suitable choice of delta phi, then in this entire interval we get something that is positive. Now, if you look at this formula, then the corresponding curve looks like this. If you just set the 0th order approximation, then you would get this red straight line. Light would propagate along this straight line, but because of this additional term, we actually get this blue curve, which initially is asymptotic to the straight line, but then changes direction and becomes asymptotic to another straight line. And there's an angle delta phi between these two lines, exactly this delta phi here. So we observe that the path of light changes in the gravitational field. For example, light that passes near sun is deflected. There's a change by an angle delta phi as illustrated here. Now we can work out what this angle delta phi is. We just have to find out what is the asymptotic direction in this direction and in the asymptotic orientation in the other direction. So what happens when r goes to infinity? Then obviously u, the reciprocal, goes to 0. And we have already seen this happens if phi goes to pi. So this is this straight line where u goes to 0. And now we have to find out for what other angle does u go to 0, which corresponds to this other direction. Now, if we assume that this effect of deflection is small, which is certainly valid in our solar system, then we can approximate this equation for a small angle phi. And for small phi, the sine phi is approximately equal to phi. The cosine is approximately equal to 1. And if you solve this approximation for phi, you find this expression here. So the delta phi without the minus sign is then obviously given by this equation here. So we find the deflection angle in geometric units is given like this. And in SI units, if you restore the g and c squared factors, we have this effect. Now, this practically means that if this, for example, is the light from a distant star, which may be somewhere here and reaches you here on Earth, then the star appears to be in a slightly different position than it actually is, because you have to look in this direction in order to see the star, even though the star actually is in this direction. And that's the effect that one can practically observe. The star, which is or where the light passes near a massive body, appears to be in a slightly different position. And that's exactly the effect that you can observe for Sun as well. If light passes just at the surface of Sun, so if d is equal to the radius of Sun, then you get that this deflection angle is 1.75 arc seconds. And obviously, it's generally difficult to observe a faint star directly near our bright Sun. But whenever there's a solar eclipse, then you can do this. Then the moon covers the bright sunlight, and you can see even the faint stars. And this was another great confirmation of general relativity in 1919, when two observations led by Eddington did observe this effect. Okay, so this was a study of the Schwarzschild solution. In the remaining time, let me quickly derive another exact solution to Einstein's field equations, which describes a simple cosmological model. Indeed, general relativity nowadays is regarded as one of the most satisfactory models of the large-scale universe that we have, so it's quite appropriate to derive cosmological models from Einstein's field equations. And we want to construct a cosmological model making the following assumptions. First of all, cosmology is a little bit different from any other science where you study some objects like, say, stars or certain animals or bacteria or whatever. Normally, you have many copies of the object that you want to study, but not so in cosmology. Unfortunately, we only have one universe, and even worse, we sit directly in the middle somewhere of this universe. So we look at the universe just from a very limited perspective. So in order to describe this complicated object where we have just one copy of, we need to come up with some reasonable principles. And one of these is the cosmological principle, which says at each time, at all spatial positions in the universe, all spatial positions in the universe are equivalent, except for local irregularities. So in other words, we assume there's no reason why we should be in a preferred position in the universe. If we happen to observe the universe from any other spatial position, then we should get the same results. So we can assume, it's reasonable to assume that our universe is spatially homogeneous. And we also observe our universe is isotropic. If we look at different directions, then we always observe the same. For example, looking at different directions, you find the same distribution of galaxies, or the cosmic microwave reaches us in the same intensity from all directions after you compensate for the motion of Earth and Sun. So there's good evidence that our universe should be described by a model which is spatially homogeneous and isotropic. If you do this, then this also very much reduces the form that our metric can have. And in suitable coordinates, it takes on the form of the FLRW metric, which is named after Friedman, Lemaitre, Robertson, and Walker. You can introduce a time coordinate t and spherical coordinates r, theta, and phi in such a way that our metric is almost fixed. We have just one unknown function a here, which is also called the scale factor. So this just indicates how the spatial geometry is stretched or shrunk as time progresses. So this corresponds to the expansion or contraction of our universe. We again see our famous spherical part of the line element. And we have in this factor k, which determines how our spatial geometry looks like. What is in the spatial curvature? Is in the 0, positive or negative? So this corresponds to the value 0, 1, or -1 for this parameter k. Our universe could be spatially flat. It could have what corresponds to a spherical geometry or a so-called hyperbolic geometry. For simplicity, let's just choose k is equal to 0 and focus on this first case. But that's likely a practically relevant situation because current cosmological observations are consistent with a value of 0 for k. So it's likely that our universe actually is spatially flat, or the spatial curvature is very small and cannot be found on small scales. So it's at least plausible to assume that k may be 0 in our real universe. So let's just focus on the simplest case. Now we still have to find the scale factor a. And for that purpose, we have to formulate Einstein's field equations. In order to do this, we somehow have to specify what the right-hand side is. And let's also say we choose our cosmological constant to be a positive quantity, which once again is consistent with observations from, say, the Planck satellite. So it may be that our universe is described in terms of a positive cosmological constant, and other people may say, no, we don't need a cosmological constant. That's just all a consequence of inhomogeneities that we don't consider in our model, but let's just come up with the simplest model where we have a homogeneous universe, but a positive cosmological constant. In order to describe the matter in our universe, let's say we want to describe this by a perfect fluid where the individual fluid particles correspond to the galaxies. Now, usually galaxies only interact via gravitation. It's rare that galaxies actually collide, which can happen, but doesn't happen too often. So one could say the only interaction is gravitation, and then the suitable perfect fluid model is called incoherent matter or dust. That's a perfect fluid where the pressure vanishes. Pressure would be related to collisions between the particles, but because this rarely happens, we have some collisionless matter, and that's a dust model. In that case, the energy momentum tensor takes on a reasonably simple form. We have the energy density of the matter distribution times UA, UB, which corresponds to the force velocity of the galaxies of our dust particles. Now, the energy momentum tensor always needs to be divergence-free, which leads to equations of motion. On the one hand, applying this to this structure of the energy momentum tensor, we obtain this equation for the force velocity, which you will recognize that's just the geodesic equation. So it turns out in this model, the dust particles in the galaxies move on geodesics of the spacetime, which is not the case for general perfect fluids, but in this particular setting, we get this result. Also, we get another equation. The time derivative of this particular expression is equal to 0, which means the density must be an integration constant divided by a cubed. And I just have renamed the integration constant in a convenient way. It looks a little bit like a mass divided by a volume, which then would give the density, but you could just call this entire expression some integration constant. So importantly, the density is proportional to a to the minus 3. Now you can work out Einstein's field equations with a positive cosmological constant and this energy momentum tensor on the right-hand side. And it turns out you get two non-trivial equations. The first one is a first-order equation for A. A dot refers to the time derivative. This is known as the Friedmann equation. And the second equation contains a second-order derivative of A. And second derivatives of the scale factor correspond to an acceleration. And therefore, this is also referred to as the acceleration equation. Okay, let's come to my very last slide for this presentation. If you solve these equations, in particular, you can, if I go back, you can replace this row here by this formula. So really the only unknown is in this function A. You can solve this and find this explicit formula for the scale factor A as a function of time t, given in terms of this hyperbolic cosine and this exponent 1/3. Now, how does the solution behave? First of all, we can see what happens if t is small. If you consider an expansion of the hyperbolic cosine for small t, you get this expression. So importantly, this shows for small t, the scale factor case is t to the 2/3, some power of t with exponent 2/3. Now, if you work out the density, where we have seen this is proportional to a to the minus 3, you get that the density behaves like t to the minus 2. And this means if t goes back in time, if you approach t is equal to 0, the scale factor goes to 0 and the density goes to infinity. So we automatically see from this model, this corresponds to a density which initially at t equals to 0 diverges. Our universe starts from a Big Bang in this model. Secondly, for this expression where we assume a positive cosmological constant, we can also consider the limit where lambda goes to 0. And now, once again, computing this limit here, you get exactly the same expression now for all t if you consider lambda goes to 0. So this shows in the early universe, we get the same expression in either case. So no matter what lambda we have in the early universe, we get the same as in the lambda equals 0 solution, which shows the cosmological constant is not relevant for the early universe. We get the same thing in the limit lambda is equal to 0 that we would have for any lambda in the early time limit. However, lambda becomes very important in the late universe. For large t, the hyperbolic cosine is approximately equal to an exponential function, and this entire expression then behaves like this exponential function. And if the scale factor is exponentially growing, this corresponds to an accelerated expansion. So automatically, in this model tells us what we actually observe in our universe. Our universe is currently in a phase of accelerated expansion. So this very simple model already shows important aspects. For time going to 0, the scale factor starts from 0 and the density from infinity. then the universe is expanding for some time, but the acceleration is negative. But then this changes, and suddenly we go into the phase where the exponential term dominates, and we end up with a phase of accelerated expansion. And for observation of this in our real universe, we in fact had the Nobel Prize. Okay, so this was a very simple cosmological model, and this concludes my third lecture. Thank you very much.
Thank you, Jörg. I haven't seen any questions come up in the chat, but do any of the students or anyone have any questions for Jörg at this point? No, doesn't look like that. In that case, it's 3 minutes to 10 at the moment. Maybe we come back, just give everybody a couple of minutes to get a coffee or anything like that, and come back at 5 past for the second half of the lecture. Awesome. Okay, see you all at 5 past. Okay, welcome back everyone. I hope you've all had a chance to grab a cup of coffee and stretch your legs. Jörg is going to continue now with the final part of his introductory lectures to general relativity. Whenever you're ready, Jörg.
Okay, thank you very much. Again, I try to share my screen. Okay, here we go. Now, this is the very last part in our 4-lecture series on Introduction to General Relativity, and this is now about black holes. You have, of course, encountered black holes in many forms in the summer school presentations already, so I want to look at some more basic properties and start with a different interpretation of the Schwarzschild solution that we just looked at in form of the Schwarzschild black hole. In the previous lecture, when I derived the Schwarzschild solution, the idea was we want to describe the exterior vacuum solution around any spherically symmetric matter distribution, for example, the field outside a star like our sun. So we have obtained this form of the line element, and here the idea is this is valid only in the exterior vacuum region of the star, so in some region where r is greater than or equal the radius of the star. If you want to obtain the full solution, including the star, then you need to solve the Einstein equations again, separately in the matter region, and for that purpose, specify the matter that characterizes the star, the stellar model that you're interested in, and afterwards match the two solutions at the surface. So that's the general procedure. You have the interior solution for the matter equations, this exterior vacuum solution, the Schwarzschild solution, and you have to match this at the surface of the star. But now we could say, what happens if we take the solution seriously for any value of r, let's say any non-negative value of r, what do we obtain in that case? Now, as discussed in other lectures, we immediately have the problem that some of our metric coefficients diverge at certain coordinate positions. We observe certain singularities. If r is equal to 2m, then 2m over r gives 1, 1 minus 1 gives 0, so here we divide by 0. On the other hand, if r is equal to 0, we divide by 0 here, which means that 2m over r goes to infinity. So we observe some problems at r equals 0 or r equals to m. Now, because of the freedom in general relativity that we can choose coordinates however we like, we have the problem that it's not immediately clear if our metric coefficients in some coordinate system blow up at certain coordinate locations, then it's not clear whether this is just due to the choice of our coordinates. So maybe we can change our coordinates in such a way that we remove such singularities, or maybe we cannot. So in the first case, one would refer to a coordinate singularity, which is just a consequence of your coordinate choice. In the second case, this is an actual curvature singularity, which is really a defect of the spacetime itself and cannot be changed if you change your coordinates. So how do you distinguish between these two? You already heard about that it is probably a good idea to look at scalars, at quantities that are invariant and do not depend on the coordinate system. And if we can construct scalars from curvature quantities, then we can characterize curvature properties in an invariant way, which is independent of our particular choice of coordinates. Chris already mentioned a particularly useful quantity, which is the Kretschmann scalar, that's obtained by multiplying RABCD with all indices down by RABCD with 4 upper indices and summation over all indices. So no free index remains. We get just a scalar. For the Schwarzschild solution, the scalar looks like this. And you can see if r goes to 0, this quantity obviously diverges. So we can be sure r equals 0 must be a curvature singularity. This quantity here is independent of the coordinate system. In any coordinate system, we would have the problem that this quantity diverges. On the other hand, if you plug in r is equal to 2m, this quantity does nothing special. So there's a chance that r equals to 2m is just a coordinate singularity. Sorry. So that's not guaranteed. It could well be that just this quantity happens to be regular at r equals to m, and some other curvature quantities may still diverge, but at least we have a chance that this is just a coordinate singularity. So the question is, if you assume the singularity of our Schwarzschild coordinates at 2m are just a consequence of this coordinate choice, how can we possibly introduce better coordinates? Well, for that purpose, let's do something which Susan already showed in her slides. Let's look at the behavior of radial light rays. This is slightly different from the light deflection that I studied previously, where we consider some motion of light rays in the equatorial plane. Here we consider radial light rays where theta and phi are both constant, so they just propagate in the direction of our r coordinate. Now, once again, using the condition that light rays are characterized by null geodesics, we have this normalization condition here. And if theta and phi are constant and only t and r change as a function of our curve parameter lambda, then this normalization condition looks like this for the Schwarzschild solution. You can easily solve for dt, and because of these squares here, you get two possible signs. dt is plus or minus this expression in terms of dr. The two signs are useful because this just means if t increases, then r could either increase or decrease, which just corresponds to the two types of either outgoing radial light rays or incoming radial light rays. Now, this expression can be simplified a little bit. If you multiply this fraction by r, then you get r over r minus 2m. And then you can write this r here as r minus 2m plus 2m. And the first term just gives a 1. And from the second term, from the 2m over this term, you get the second term. And now you can easily see that it's not a problem to integrate in this equation. If you integrate on the left-hand side, you get just t plus a constant. And on the right-hand side, you get an r here and a logarithmic term from here. So if I denote the integration constant by w, then we've got these equations for our two families of either outgoing or ingoing null geodesics or light rays. And if I choose different values for this integration constant, this just corresponds then to a different light ray. So for each light ray, this constant is just a fixed value. Now, if we plot this, then we obtain the following diagram, which you have seen before. On the x-axis, I have r, or more precisely r over 2m, in order to get something dimensionless. And here I plot t over 2m. The red curves correspond to the outgoing light rays, and the blue curves are the ingoing light rays. And obviously, where this argument is 1, where r is equal to 2m, something special happens. So apparently, these light rays are not very nicely described in terms of our Schwarzschild coordinates. So the idea could be to change the coordinates by just choosing one of these two families of light rays, either the red curves or the blue curves, the outgoing or the ingoing null rays, and adapt coordinates to this. So we can choose a coordinate transformation where we choose our integration constant w, which is a constant on each of these curves, as a new time parameter. For example, if you would choose these blue ingoing curves, then in order to go from curve to curve up in time direction, the value of w needs to increase. So it's reasonable to use this as a new time coordinate. So we can replace our t by w, and depending on which family of geodesics, the red or blue curves we choose, we get what is either called the retarded or the advanced Eddington-Finkelstein coordinates. Let's say, as an example, we look at the advanced one, which are adjusted to the ingoing light rays. Then our equation was like this. And if we now introduce w as a new coordinate, we can work out the differentials. dt is equal to dw minus the r derivative of this times dr. And we have previously obtained this by integration. So if we differentiate, we just recover what we had before. We get this expression. Now we can replace dt everywhere in the Schwarzschild line element in terms of dw and dr. So if we do this, the dt squared now becomes the square of this term, and the other terms are unchanged. Now if you work out the square, one term that you get is the dr squared divided by the square of this term. One of these cancels because of this factor, and with this minus sign, you get exactly the negative of this term. So all dr squared terms actually disappear. We just from here get a dw squared term, and then we get a mixed term if you multiply the dr and dw terms, which looks like this. Now in this form, the metric obviously is regular if r is equal to 2m. The only thing that happens is at r equals 2m, this coefficient becomes 0. But because we still have this mixed dw dr term, even if you write down the matrix representing the metric, this matrix does not become singular at 2m. It's still invertible even at this point. The determinant does not vanish. So that's now a regular representation of the Schwarzschild solution. We can repeat the calculation of radial null geodesics, and you would obtain these red and blue curves. So what I'm showing here is as a function of, again, r over 2m. I'm not quite showing the coordinate w, which would be a so-called null coordinate, which is adjusted to these light rays in the RW coordinates, these red curves are simply given by W is equal to a constant. So this would correspond to a horizontal line. It's slightly nicer to have something like a time coordinate where these rays actually propagate upwards in time direction. So if I, rather than W plot W minus R here, then I achieve that these red curves are not horizontal, but have these 45-degree angles, which is just a little bit nicer for the picture. So you can see in these coordinates, the ingoing light rays look very nice, are given just by these simple straight lines. To describe the other family of light rays in these outgoing blue curves, you still get some terms which still involve logarithms. But at least one family of light rays looks very easy. What I'm also showing in this picture, similarly to what you saw in Susan's talk, is some light cones, these light cones here. So what is a light cone? Just imagine you send a pulse of light at your spatial location, then this will propagate with the speed of light in any direction. So the light front will move on a sphere that gets larger and larger. If you suppress one dimension, if you just consider two spatial dimensions, then it's not quite a sphere, but a circle which gets larger and larger. Now, if you show this in a space-time diagram, you add time as a third dimension. So these circles do not only get larger, but they also move upward in time direction. So altogether, they form such cones. So here you send the light signal, then the circles get larger and larger and move upward in time direction. So that's just illustrating how light propagates. And obviously, the light would propagate either along the blue curve here or along the red curve. And I've just extended this to a somewhat three-dimensional picture here. So this is the meaning of these light rays. This shows how light propagates from this point or from this point and so on. Now, if you don't have light, but if you have something like a particle, an observer, which moves on a time-like geodesic, then necessarily this curve, if it goes through this point here, needs to move through the interior of the light cone. It could not possibly go like this along the outside of the light cone. This would correspond to motion with more than the speed of light, which is not possible. It necessarily needs to go through the interior of the light cone. So the light cone does not only tell you something about the motion of light, but also about particles or observers. They need to go through the interior of the light cone. Now, in these four examples of light cones, you can see as you approach this line, where R is equal to 2m, the light cone bends more and more to the left. And eventually, if you want to go through this point, then the only possibility is you start outside this blue line, go through this point, and you end up in this region here, where R is less than 2m. So this entire surface here, where R is equal to m, behaves like a one-way membrane. You can only cross this in one way, namely from the exterior to the inside, not the other way around, which would require more than the speed of light. So this is not possible. This shows that the Schwarzschild solution does indeed describe a black hole, and because it's a spherically symmetric solution, it's a spherically symmetric black hole, and the surface here is also called an event horizon. Anything that happens in this interior region, where R is less than 2m, cannot be observed by the outside, so you could not see any events going in here, because nothing can escape from this region, as you can see from this light cone structure. So that's what defines this black hole. It has a surface, this event horizon, and this is a one-way membrane which you can only cross from the outside to the inside. So once someone is unlucky enough to enter the black hole, it's not possible to ever come back. And as we know, at R equals 0, we have a curvature singularity. So if somebody goes inside this black hole, he would enter this region where the curvature singularity is. Also, it turns out if you are outside the black hole and have a rocket ship, then you could still fire the engines in order to remain at a constant spatial position. But as soon as you are inside the black hole, then there's no way to avoid that after a finite proper time, you reach the singularity, no matter how you fire the engines. And the maximum amount of time is given by pi times m, where m is the mass of the black hole. So there's a finite period of time in which you necessarily reach the singularity once you are unlucky enough to be inside the black hole once you have crossed the event horizon. But as we also heard about, even before this happens, there are so strong tidal forces which would already rip you apart, so you would not even survive to enjoy this moment when you reach the singularity. Now we've introduced these Eddington-Finkelstein coordinates. I showed you the picture for one of the two types, and I mentioned one family of geodesics looks very simple in these coordinates, but the other family does not. One family is much more complicated. So it would be nice if we could come up with coordinates where both families of geodesics look very simple. Let's again write down the equations for the outgoing and ingoing geodesics. And here I introduce a different name. Rather than W, I call the first parameter U. And for the other family, I call this W parameter now V. And outgoing geodesics are now characterized by U as constant. Ingoing geodesics have that V is constant. Now we could have an idea. Let's just do a coordinate transformations where we do not only replace one of our coordinates, but actually both of T and R in favor of two new coordinates, namely U and V. So then we describe both families of geodesics in a nice way. Then U equals constant describes one type of geodesics, V equals constant the other one. So let's do the following coordinate transformation in 3 steps. And let's initially assume that R is greater than 2m, so we don't need this absolute value here, and the calculation is a little bit simpler, and afterwards the final result turns out to be valid for all values of R. In the first step, you replace T and R by U and V according to this transformation formula. So that's the formula which tells you how U and V look like in terms of R and T. We can also try to work out in the inverse transformation. If you simply add the second equation plus the first one, then this lengthy term here disappears, and you can solve for T. T is just V plus U half. It's slightly more complicated for R. If you instead subtract the 2 equations, you get rid of the T, and you find that this expression, depending on R, is given in terms of U and V like this. Now, this is an unpleasant expression where you cannot explicitly solve for R, at least not in terms of elementary functions. It turns out if you define suitable special functions, in this case, the so-called Lambert W function, you can write down a formal expression for R as a function of U and V, but still you can just take this as an implicit definition of R in terms of U and V. In the next step, we can change our null coordinates U and V. And by the way, they are called null coordinates because if either U is constant or V is constant, we describe one of our 2 types of null rays, of light rays, which point in null directions. Therefore, these are called null coordinates. If we replace U by any function capital U, which only depends on the little u, and V by any capital V, which only depends on little v, then it's still correct. If little u and V or V are constant, then also the capital versions must be constant. So null rays would still described by the condition that U is constant or V is constant. So we can make this transformation in U direction and in V direction. The particularly convenient choice is to introduce these exponential functions in order to obtain a nice form of the final metric. Finally, it's nicer to have a time coordinate and a space coordinate, say t and x, rather than these null coordinates, where in a diagram light again propagates in an upward direction rather than in a horizontal or vertical direction. And we can simply rotate our coordinates with this transformation and replace u and v in terms of t and x like this. Now, if you start from the Schwarzschild solution and go through all of these transformation steps, then let me just show you the final result. We obtain the Kruskal metric, or more precisely, the Kruskal form of the Schwarzschild metric, which looks like this in terms of a time coordinate t, a spatial coordinate x, and angles theta and phi. Now, we still have our original r here, but now we can go through the steps in the coordinate transformation and work out this r should now be considered to be a function of t and x, and it's defined implicitly through this equation. Once again, if you want to use the Lambert W function, you could write down an explicit formula for R, or you just take this as some formula which defines R, and maybe for any value of t and x, you can solve numerically to find the corresponding value for R. Now, this metric is also regular at the event horizon of the black hole, and you can obtain this picture here describing the spacetime in x direction and t direction. So that's a tx diagram. I'm not showing any of the angles because nothing depends on these angles. Now, first of all, which values of t and x are allowed? Recall that at r is equal to 0, we have a curvature singularity. So first we should find out where in this diagram do we have that r is equal to 0. If you take this formula here and plug in r is equal to 0, the exponential function gives a 1. So with the minus sign, we have a minus sign. This term disappears. Here we have another minus 1. So we get the simple equation t squared minus x squared is equal to 1. For any t and x values where this is satisfied, we have that r is equal to 0. And this just corresponds to 2 branches of a hyperbola, namely this branch here and that branch here. So that's the location of r equals 0, where we know we have a curvature singularity, and the Kretschmann scalar blows up. everywhere in between these two hyperpolar branches, you get positive values for R, so that's the actually allowed region. So we have to dismiss everything above this line and everything below this curve. That's not a region which is accessible because we would need to cross a curvature singularity, which is not possible. So we are confined to the range between these two lines. And by the way, any other value of constant R either gives you a positive or negative constant here on the right-hand side. This corresponds to other hyperpolars looking like this, or hyperpolars like this, which show in the other orientation. So that's how lines of constant R look like. What is in the special line where R is equal to 2m? If R is equal to 2m, this term gives a 1, minus 1 gives 0. So we have t squared minus x squared is equal to 0. If you solve for t, then t is plus or minus x. We get two possible signs because of the quadratic equation. So either we get this straight line with a slope of plus 1, or that straight line with a slope of minus 1. So that's where we have R is equal to 2m. And we have seen previously at R equals 2m, we have in the event horizon of the black hole, the surface of the black hole. Now, first of all, let me repeat, the metric is regular everywhere in between these two curves where R vanishes. So this metric also shows that there is no singularity at the position where R is equal to 2m. This was just something that we observed in the Schwarzschild solution, but there's nothing physically happening. Secondly, in this diagram, which was based on our construction adjusted to the two families of null rays, light now propagates along straight lines with slopes plus or minus 1. So if you would draw anywhere in this diagram the light cone, this would just look like a normal cone where the two sides have angles of 45 degrees. So it's just very nice light cones everywhere here. Now let's have a look at the different regions 1, 2, 3, 4 shown in this diagram. Region 1 is just our normal exterior universe outside in the black hole, which corresponds to R greater than 2m in the original Schwarzschild solution. That's in the region 1 here. Then this surface here at R equals 2m is in the surface of the black hole, the event horizon, and in the actual black hole is contained in region 2 here. So that's the black hole region. But as you can see in this picture, we actually have more than we could see in the original Schwarzschild coordinates. This is also referred to as the maximal analytic extension of the Schwarzschild solution, which contains as many regions as you possibly can include. What is in this region 3 here? This is somewhat symmetric to the black hole region, but there's an important difference. If you look at the surface of the black hole, the event horizon, and you draw a light cone here with the nice 45-degree angles, you can see a point on the event horizon can only be crossed from the outside to the interior of the black hole. So once again, we see things can only fall into the black hole, but not come out. But for the white hole, it's quite the opposite. If you draw a light cone here, you can see a point on this surface can only be crossed starting from the interior region to the outside. That explains why this is called a white hole. It behaves like the opposite of a black hole. In a black hole, things can only fall in. For a white hole, something can only come out. It's only possible to come from this region into that one, but not the other way around. Therefore, this is referred to as a white hole. And we have yet another region, this region number 4, which looks like a mirror image of region number 1. Well, this behaves very much like region number 1. It has the same kind of geometry. It's another asymptotically flat region, which far away approaches Minkowski space. So in a certain sense, our universe here, the exterior universe outside the black hole in region 1, is connected in this picture here to another universe, another asymptotically flat region. But I should immediately point out, if there was any observer in this universe here and tries to send a signal into region 1, then if you draw a line from here to here, this would have a slope which is too small. It would be outside the light cone. It would require more than the speed of light to send a signal from here to here. So actually no communication is possible between regions 1 and 4. The only thing you could possibly do is fall into the black hole, and if somebody from region 4 also falls into the black hole, you could quickly meet this person in the black hole region before you both end up in the singularity, but then maybe you end up going there and nobody else is there, so probably better don't try. Okay, so that's the structure of this Kruskal diagram. And let me just point out two differences between the singularity here in the black hole and the white hole singularity. The black hole singularity is also referred to as a future singularity, because if you have any observer entering the black hole region and necessarily reaching the singularity is always in the future of this observer. But if you had someone come out from this white hole region, then necessarily there's other singularities in the past of this observer. So that's all the regions that we possibly can get if we introduce the Kruskal coordinates, the maximal analytic extension of the Schwarzschild solution. The question is, are these regions, the white hole region and the other universe, actually physically reasonable? If I go back to this picture, this is the Schwarzschild black hole, which assumes that we have a black hole which does not change. It always has been there, always will be there. That's not quite what we have in a physically realistic situation, where we maybe initially have a star, which then collapses at some stage and eventually forms a black hole. So that's a little bit different. If I draw it into this diagram, then the surface of the collapsing star will form maybe a trajectory like this. And then everywhere outside here, we do indeed have vacuum everywhere outside the star. So the Schwarzschild solution is still valid here. We know this from Birkhoff's theorem. The exterior of even a collapsing star in spherical symmetry will be described by the Schwarzschild solution. But everything inside the star will not be a vacuum solution to the Einstein field equation. So we have to dismiss everything here. This is not given by the Schwarzschild solution. Instead, we need to solve the Einstein equations again with some matter source to find what the interior actually looks like. So in other words, in a realistic gravitational collapse, only a part of region 1 and a part of the black hole region 2 would be realized. Everything else will be something different depending on the type of matter in your star. Therefore, it's likely that only our exterior universe and the black hole solution are actually realized in our world, in our realistic universe, and the white hole and the other asymptotic universe is just a mathematical artifact of this completely time-independent solution, where we have the black hole at all times and it's not formed in some gravitational collapse. So likely, white holes are just hypothetical objects and do not exist in nature. Okay, now if we assume that a black hole is formed in a gravitational collapse, then obviously what happens if the star is non-rotating, then this original star is spherically symmetric, and if this collapses to a black hole, it will form a spherically symmetric black hole. But in reality, stars are not exactly spherically symmetric, they are actually rotating, and if a rotating black hole collapses, it will not obviously form if a rotating star collapses, it will not form a non-rotating spherically symmetric black hole. So usually stars are well described in terms of something that is still axially symmetric. So it's independent of phi rotations, but it does depend on the theta angle. So it's not spherically symmetric anymore. So we should expect that a collapsing rotating star forms an axially symmetric black hole, which is not quite spherically symmetric, but only has the symmetry in phi direction. Now, the corresponding solution, obviously, as you know, was found by Roy Kerr in 1963. That's the famous Kerr solution. At this stage, also a warm welcome to Roy, who I see has joined us today. And hopefully I don't say anything embarrassing about your solution, but now I'm going to discuss it. The solution is practically particularly relevant because we have an important result which says that is the unique black hole solution. The only stationary asymptotically flat vacuum black hole is indeed given by this Kerr solution, which means any star that collapses to a black hole has no other chance than eventually approaching this Kerr solution. So initially, say if a star collapses or if two neutron stars probably merge into a black hole, you obtain an object, a black hole, which is still highly dynamic and will emit gravitational waves, will be wobble around. But eventually energy will be lost because of the gravitational waves, and this will settle down to an equilibrium state. And because we only have this unique equilibrium solution, the Kerr black hole, necessarily the final outcome should be the Kerr solution. Now for the Schwarzschild solution, I showed you in some detail how you obtain the solution by just working out Einstein's vacuum equations, starting from an adjusted form of the metric, using some coordinate degrees of freedom and so on. And eventually it was not too complicated, eventually by just solving ODEs to find out how the solution looks like. This is much more complicated for the Kerr solution. So here, let me just quickly comment on a few different approaches how you can obtain the solution in principle without going into any details. If you wanted to follow the same route, you could now write down a form of the metric where the metric functions do not depend on the radial coordinate only, but at the very least also on the angle theta, because our solution is not spherically symmetric anymore. It will only be axisymmetric. So you obtain a complicated system of PDEs that you could try to solve, but that's really involved. So maybe this is not so successful. There's another approach, the so-called Newman-Chennes trick. You could start from the Schwarzschild solution and very roughly speaking, apply something like a complex coordinate transformation, a coordinate transformation involving complex numbers. So it's a little bit more involved, but roughly it's a complex coordinate transformation. And even though normally coordinate transformations are supposed to be real functions, if you do this with complex functions, you can, in the end, produce the Kerr solution starting from the Schwarzschild solution. So it's interesting. Somehow, these two solutions are connected via a complex coordinate transformation. Or you can look for algebraically special solutions where the curvature quantities, in particular, the Weil curvature tensor, a certain part of the Riemann tensor has certain algebraic properties, and then try to work out solutions which have a particular algebraic property. Or you can apply some methods from soliton theory. So soliton theory is the treatment of certain nonlinear partial differential equations which are integrable in a certain sense. And there's a technique which would allow you to start from this flat spacetime, Minkowski spacetime, and apply a so-called Backlund transformation, which eventually transforms this flat solution into the rotating black hole solution. So you can obtain the Kerr solution from a so-called Backlund transformation. Or there's a way to formulate the Einstein vacuum equations under the assumption of axisymmetry into just a single complex equation and solve this with another method from soliton theory, which is called the inverse scattering method. So you can solve a certain boundary value problem. You want to describe a black hole solution, and then there are techniques from soliton theory to deal with this complex Ernst equation. So that's many approaches which would all allow you to obtain the solution, and each approach is not that easy. So this certainly goes beyond what we are doing here. Therefore, I just show you the final result. You can write down the Kerr solution in different coordinate systems. We will encounter another one shortly. But this coordinate system here, the so-called Bayer-Lindquist coordinates, is somewhat similar to the Schwarzschild coordinates that we used earlier for the Schwarzschild solution. So here we have again a time coordinate t and spatial coordinates r, theta, phi, something which somewhat behaves like a spherical coordinate system. Now we've got this dt squared term here. Here we have a linear combination of dt and d phi, and this expression is squared. So if you expand, you get a dt squared, a d phi squared, and also a dt d phi term, which we didn't have for the Schwarzschild solution. So that's something that you usually encounter for such rotating solutions. From here, you get a dr squared, d theta squared, another d phi squared. So that's the structure of the solution. There are some abbreviations. This delta, which appears here, is just r squared minus 2mr plus a squared. M is the mass of the black hole, and I will define a in a moment. And another abbreviation, the sigma here, is an abbreviation for this quantity. Oh, sorry. Now, the solution now depends on two parameters. Recall the Schwarzschild solution only had one degree of freedom, just in the mass of the black hole. We only had the parameter m. But for this solution, we have a second parameter a, which describes the rotation rate of our rotating black hole. So strictly speaking, that's j, the angular momentum divided by the mass, angular momentum per mass. And if you know a and m, you can just recover the angular momentum if you calculate the product am. In order to somehow get a feeling for this solution and understand this, let's just first look at two special cases. How does the solution simplify if we choose both parameters to be equal to 0? If we do this, then this entire term vanishes if m is equal to 0. Also, the sigma will be equal to r squared. The delta will be equal to r squared as well. So sigma over delta is just 1. And here we get a dr squared term. This is r squared. Here we get a r squared d theta squared. And here we get r squared sine squared theta d phi squared. So in other words, what we find is just Minkowski spacetime in spherical coordinates that's obtained as the limit a and m both going to 0. What happens if m is not 0, but a goes to 0? If a goes to 0, this term here becomes an r squared sine squared theta d phi squared. Then here we have a minus tt squared. The sigma is still equal to r squared. So here we get 2mr over r squared. Over r squared, which gives 2m over r. And if you factor out the dt squared from here, you get minus 1 times 1 minus 2m over r times dt squared, exactly what we had for the Schwarzschild solution. This term disappears. And here, the delta over sigma becomes again 1 minus 2m over r squared. So this just transforms into the Schwarzschild solution in Schwarzschild coordinates, which shows these Lindquist coordinates are closely related to the Schwarzschild coordinates, and the limit a equals 0 when the black hole is non-rotating. This reduces to the Schwarzschild solution in the Schwarzschild coordinates. Now the solution still has some symmetries. It's not spherically symmetric, but it is stationary, which means if you shift your time coordinate, then nothing changes. None of these metric coefficients depend on t. And if you shift t, then the dt does not change. The differential of a constant is 0. So the solution is invariant under time translations. And also it's axisymmetric. It does not change if you increase your angle phi for the same reason. Nothing here depends on phi, and the d phi does not change if you add a constant to phi. It also has two discrete symmetries. If you would replace the time coordinate by its negative, then in case of the Schwarzschild solution, nothing changes. You still obtain a spherically symmetric black hole. For this solution, however, if you only change t into its negative, then the dt d phi mixed term would change its sign, and that's expected. Then you still obtain a black hole, but it's now rotating in the opposite direction if time goes backward. So if it initially rotates in one direction, if time goes backwards, it will rotate in the other direction. And therefore, the solution is not invariant if you replace just t by its negative. But if you both replace t and phi by its negative, then first the time goes backward and the black hole rotates in the other direction. But then you also measure your angle in the other direction. Then you recover the original solution. Or you can replace t by its negative and the rotation parameter a by its negative, and then you also get the sign change here from a and here from the dt, and because you square, this doesn't matter, so the solution is also invariant under this change. Furthermore, the metric in these coordinates obviously would be singular when either delta is equal to 0, because then we divide by 0 here, or when sigma is equal to 0, when we divide by 0 here. Now, what happens at these surfaces? For the Schwarzschild solution, it was a good idea to look at this invariant quantity, the Kretschmann scalar. And here, the full formula is a little bit too complicated, but roughly it has the structure a complicated expression divided by sigma to the 6. So this shows if sigma goes to 0, certainly something happens, and therefore we expect a curvature singularity at surfaces where sigma vanishes. But if you plug in delta is equal to 0, nothing special happens. So this is expected to just show us where the event horizon is. It's just a coordinate singularity in these coordinates. Let's first have a look at this curvature singularity at the surface where sigma is equal to 0. And this was just an abbreviation. Sigma was an abbreviation for this term here. Now, if we did have the non-rotating black hole, if a was equal to 0, then r squared would vanish when r is equal to 0. Now it's slightly more complicated. Here we have a sum of two squares whenever a is not equal to 0, which can only vanish if both terms individually are equal to 0. So this requires that r is equal to 0, but also to make sure that this term vanishes, theta must be equal to pi half if a is not equal to 0. So that's a little bit unusual. If r and theta really were just normal spherical coordinates, then r equals 0 would correspond to a single point, the center of the coordinates, and it wouldn't matter what value theta has. So obviously, these coordinates are not quite spherical coordinates in the usual sense. It's a little bit more complicated, and the structure of the singularity is a little bit more involved. We will come back to this in a moment. Also, we have coordinate singularities where delta vanishes, and delta was an abbreviation for this. So the condition that this vanishes is simply a quadratic equation for r, which has these two solutions, which are denoted by r plus, the larger one with the plus sign, and r minus. Now it turns out r being equal to r plus really corresponds to the surface of the black hole that describes the event horizon. On the other hand, the other solution r is equal to r minus is a similar surface, which is often referred to as the inner horizon or the Cauchy horizon. Now obviously, this is only true if r plus and r minus, as given by this expression, are two real numbers. So obviously, we only obtain two real solutions to this quadratic equations whenever a squared is less than m squared. So we get something positive under the square root. Then if the black hole is not rotating too fast, if a is sufficiently small, then we get two distinct real solutions to this quadratic equations. And in the special case, where a squared is equal to m squared, then the square root just gives 0 and r plus and r minus will coincide. Then we get a double real root. And if finally a squared was larger than m squared, we get just complex solutions, which are physically not relevant. Then we don't have any real solutions at all. Now, there are different names for the solutions that we get in these different cases. If a squared is less than m squared, then the black hole is referred to as the non-extreme or sub-extreme Kerr solution. This really does have an event horizon, so it qualifies as a black hole. A black hole is characterized by existence of this event horizon, and then we get the solution R plus as a real solution. If a squared is equal to m squared, then we still have a real solution here. It's a double real root, and this is referred to as the extreme Kerr solution. And because this still does have an event horizon, it's still a black hole with an event horizon. But finally, if a squared is larger than m squared, then we don't get any real solution. The corresponding mathematical solution to the Einstein equations is also referred to as the over-extreme Kerr solution. And now we have in the situation, we still have curvature singularities where sigma goes to 0, but in this time, this is not hidden behind an event horizon, so you could actually see the singularity. So it's also referred to as a naked singularity. There's a famous conjecture by Roger Penrose called the weak cosmic censorship hypothesis, according to which singularities are always hidden from observers at infinity by event horizons. So the assumption is that in physically reasonable situations, we should not have naked singularities. We should just have black holes where the singularities are hidden. So if this is true, if this hypothesis is true, then the over-extreme Kerr solution would just be a mathematically interesting solution, but not relevant in nature. Black holes of this type, or it's not a black hole, then naked singularities of this type probably should not exist. So likely only the non-extreme Kerr solution is physically relevant. The extreme Kerr solution could probably be considered to be something like a formal mathematical limit. It turns out if you start from a sub-extreme Kerr solution and try to accelerate the black hole by shooting particles into the black hole, which carry some angular momentum, then you can come closer to the extreme Kerr solution, but not ever reach it. So it's something like a mathematical limit, which likely may not be realized in nature as well. So probably only sub-extreme Kerr solutions describe realistic black holes in our real universe. Okay, let's have a closer look at the singularity now, where we have seen if sigma goes to 0, the Kretschmann scalar blows up. It's possible to reformulate the Kerr solution in a different coordinate system referred to as Kerr-Schild coordinates, which looks somewhat similar to Cartesian coordinates at large distances. We have a time coordinate tau and spatial coordinates x, y, z. The actual coordinate transformation from Boyer-Lindquist to Kerr-Schild is a little bit involved, so I'm not going to write this down in detail, but I'll just give you the final result. In these coordinates, the Kerr solution looks like this. A first term is just the Minkowski line element in Cartesian coordinates, but then you have this additional term, a linear combination of dx, dy, dz, and d tau, which is squared. So it's an interesting structure of the solution. And the coordinate r, which still appears here, now should be considered to be a function of x, y, z, and it's implicitly given via this relation, which would follow from the explicit coordinate transformation. So it's a biquadratic equation for r whenever x, y, and z are given. We can reformulate this equation a little bit. If you isolate this x squared plus y squared term and divide by r squared and also r squared plus a squared, then you can rearrange into this equation, which shows that whenever r is constant, so this would be constant and that would be constant, this really just describes confocal ellipsoids. And you can read off what the semi-axes are. The square root of this, so x squared over this term here, the square root of this gives the first semi-major axis. It's symmetric in x and y, so we get the same in y direction. And in z direction, the square root of this gives r. So we have ellipsoids with these three semi-axes. And you can see if r is large, then you can ignore this a squared here, and this is approximately equal to r. So you get r, and the ellipsoid becomes approximately a sphere far away from r equals 0. On the other hand, if r goes to 0, then this semi-major axis goes to 0, but not the other two. They approach the absolute value of a. So what happens in the limit where r goes to 0 is we approach a disk with radius given by the absolute value of a. And if you look at the explicit coordinate transformation, and it's probably also clear from symmetry, theta is equal to pi half corresponds to the rim of the disk. And we know we have the singularity where sigma vanishes, which happens where r goes to 0, and also where theta goes to pi half. So this will correspond to the rim of the disk. So what we find is the Kerr singularity actually has the topology of a ring. Now, before I try to show you a picture which illustrates this, let's also look at another interesting surface in the Kerr solution, which is called the static limit surface. Assume you sit somewhere in a rocket ship outside the Kerr black hole. You can always fire your engines if the rocket is sufficiently powerful in such a way that you remain at a constant spatial position. So in our original Bayer-Lindquist coordinates, the position of such an observer as function of its proper time. The time coordinate would still change, but not the spatial coordinates. They would be equal to some constants r0, theta 0, and phi 0. Now, if you work out the tangent vector to this curve, the four velocity, you just differentiate with respect to tau. And because these three are constants, you get three zeros and just something non-trivial in the time component. We also know for an observer, the four velocity should be a time-like vector. So certainly the norm of UA should be negative. In fact, if you choose the parameter tau, it should be equal to -1, but here it's sufficient to observe it should be negative. Now, if you work out explicitly what this means, because only the time component of the four velocity is non-zero, you get just one term, which has the time component of the metric, and this must be negative. Now, because this square is positive, this tells us that GTT must be negative, and the explicit formula for this metric coefficient is given like this. The sigma is positive outside in the singularity, so this coefficient is negative, and therefore our condition is the terms in brackets must be positive. Now, that's only possible if R is either sufficiently large or sufficiently small. If you solve that this is equal to 0, you have a quadratic equation. You get two solutions, S plus minus, which look like this. And only if R is either greater than S plus or less than S minus, this quantity would actually be positive. So what happens is, as soon as you would cross in your rocket ship the surface given by R is equal to S plus, then it's not possible anymore that you remain at a constant spatial position. You are automatically tracked in phi direction. So the space-time in a certain sense is tracked around the black hole, and you cannot remain at this constant spatial position inside the surface. Therefore, this is called the static limit surface. Static observers do not exist beyond the surface. And by the way, if you compare the formula for S plus, M plus the square root to the formula for the event horizon at R plus, then we had almost the same, just without the cosine squared theta term. Then this S plus is always a little bit larger than the R plus, because here you subtract a little less from the M squared. Just if theta is equal to 0 or pi at the poles of the black hole, you would get the same expression. So this surface S plus is sitting just outside the event horizon R plus. Okay, now let me try to give you an image of all these surfaces. Based on the Kerr shield coordinates, and I choose a black hole which is rotating quite quickly to make sure that you can nicely see this and the surfaces are not too close to each other. First of all, this blue surface here, this is the static limit surface. So once you cross the surface, then static observers do not exist. You are necessarily tracked in phi direction. Then this red surface here, this is the event horizon. So once you go through this surface, you cannot come back anymore. Then further inside, the other red or purple surface corresponds to the so-called inner horizon, the Cauchy horizon. And here we have another blue surface corresponding to R is equal to S minus. That's the other static limit surface. So if you go further through this surface, then static observers actually do again exist. So just in between these two surfaces, you don't have these static observers. And finally, yellow, this is the disk, corresponding to sigma is equal to 0, and in particular, sorry, not sigma is equal to 0, but R is equal to 0, and here particular on the rim, theta is equal to pi half, so that's actually where sigma vanishes, so this is the location of the curvature singularity. Okay, so this was some impression of the Kerr solution, and finally in the last few minutes, just in this very last slide, where I just mentioned a few generalizations of the Kerr solution. Our Kerr solution does have two parameters. It depends on the mass m and the rotation rate a. If you want to, you can introduce additional degrees of freedom. For example, it's also possible to look at electrically charged black holes. Now, if you do this, then your solution will also involve electromagnetic fields. So you don't exactly have vacuum anymore, but you have what is called electrovacuum. You don't have any matter, but electromagnetic fields. In that case, if you want to obtain such a solution, you don't have to solve the Einstein vacuum equations, but actually the Einstein equations with an energy momentum tensor corresponding to an electromagnetic field. So in this way, you can construct solutions describing charged black holes. It's physically probably not that relevant, because even in stars, electromagnetic fields are important, but overall a star is generally more or less electrically neutral. So if a star collapses to a black hole, you would obtain to get a black hole which at most may have a small charge or probably be electrically neutral. And secondly, you can also solve the Einstein equations with cosmological constant. So it's also possible to derive black hole solutions where the parameter lambda in the Einstein field equations is not equal to 0. Now, the first of these generalizations was constructed in 1916, the Reisner-Nordström solution. This extends the Schwarzschild solution, and in addition to the mass parameter m, we also get an electric charge. So that's a charged black hole in spherical symmetry. Then the Schwarzschild de Sitter solution, or Schwarzschild anti-de Sitter solution, was found in 1918. Again, an extension of the Schwarzschild solution. In addition to m, it does now contain a positive or negative cosmological constant. And usually solutions with a positive cosmological constant are referred to de Sitter solutions, and with negative as anti-de Sitter solutions, and therefore this name Schwarzschild anti-de Sitter solution. Then in 1965, the Kerr-Newman solution was constructed, which generalizes the Kerr solution and does have an additional parameter Q. So that's a charged version of the rotating black hole. And finally, the Kerr-Newman anti-de Sitter solution, which has all 4 parameters, mass, rotation rate, charge, and cosmological constant, looks like this. So I'm just showing you the formula for this one solution, because all the other ones can be obtained from this one by setting some parameters equal to 0. The structure is somewhat similar to the Kerr solution. You still have coordinates t, phi, r, and theta, and the coefficients are somewhat similar. We still have our quantity sigma, which looks the same as before. We still have our delta here, but it's now slightly longer than before. We have an additional term depending on the cosmological constant, and also a term coming from the electric charge. And we have these 2 quantities, delta theta and psi, which are equal to 1 for case of the Kerr solution, but otherwise are non-trivial for this full solution. So that's how this general black hole solution looks like. But as I said before, the most physically relevant case is the Kerr solution itself, just depending on the parameters m and a. Q and lambda are interesting, but probably not so practically relevant for black holes in our real universe. Okay, this concludes the crash course on general relativity. Thank you very much for your attention.
Thanks, Jörg. I think there's a question in the chat. Do you want to read that out?
So let me just stop the screen share so I can open the chat. Energy momentum tensor. Does this require the source of gravity to be liquid-like and in motion? How can a large solid object be modeled by the energy momentum tensor? Yes, so in many cases, the energy momentum tensor is much easier applied to liquids or gases, where you really have matter flowing around. You can describe this in terms of densities, pressure, flow velocity, and so on. There's also a theoretical description of solid states in relativity, but this is much more complicated, because in relativity you cannot have perfect solids which are really rigid everywhere, because then if you would move this body at one end, the other end would start moving immediately as well. So this information of suddenly putting this object into motion would propagate instantaneously from one end to the other. So you can imagine the description of rigid bodies is somewhat involved. It's still possible, but in many cases, the energy momentum tensors indeed describe something like fluids, where you really have particles moving around.
Cool. I think that answered that one. Do we have any more questions before we break for morning tea?
And I just see another question in the chat, the lowercase m and uppercase m. I tried to consequently have the uppercase m everywhere. It is just convention. The lowercase m, if this still is somewhere, was supposed to mean the same.
Cool. Awesome. Okay. Well, in that case, I think
Emily, can I briefly say, I wanted to come back to Mia's question yesterday about the gravitational waves and the difference to the electric or electromagnetic waves. My answer was not completely satisfactory, at least not to me. And so I think what one can say is that when we look at the gravitational waves, this is like looking at electromagnetic waves in the form of potentials. So you recall that in my talk I talked about the metric as being similar to potentials, and the electromagnetic waves are expressed in terms of the electric and magnetic fields. So if we would do something similar to the gravitational waves, which one can do, and that is taking derivatives of this metric, this h that I have described. In the case of gravitational waves, you have to take two derivatives, then you end up at the level of curvature. And the part of the curvature that is relevant here is the Weyl tensor. And when you describe the waves in terms of the Weyl tensor, then you get exactly the same structure as for the electromagnetic waves. In fact, you get an electric and a magnetic part of the Weyl tensor, and they behave in exactly the same way. The equations that you get are almost identical to the Maxwell equations. So the difference that comes about in the representation of the gravitational waves is simply that we are looking at this as if we were looking at the electromagnetic waves in the form of potentials. So there is no real difference between those two. You just have to look at the right quantities. So that's all I wanted to say.
Cool. Then we've just got one new message. Oh no, that's just Mia. Thank you, she says. In that case, we will break for morning tea, and we're supposed to resume at 11:30. I think, is Jan chairing the next session, Jörg?
I think so, yes.
Cool. I'm not sure if she's here yet. Awesome. See you all back at 11:30.